Now I would like to introduce the panel members that are here with us today. First, Jill McGuire, the Director of NASA's Exploration and In-Space Services, or NExIS. Ms. McGuire will act as our moderator and a panel member during today's event. Joining Ms. McGuire, we have Justin Cassidy, Platform Payloads Office Deputy with NExIS, and Mark Newman, Systems Lead and Hardware Manager for the RRM-3 payload in NExIS. Please help me in welcoming the panel members today. Please take it away.
Thank you. So I wanted to start today by paying honor to the grandfather of satellite servicing, Mr. Frank Ceppolina. He started every presentation he ever gave by saying, "Where were you in 1980?" So I figured I had to just get that in there because in his mind, servicing started back in 1980 with Solar Max. And that was when the ideas and how do we actually service, how do we bring satellites back to life came about. And so the whole time he was at Goddard doing Hubble servicing missions and leading us into where we are today with NExIS, that was his goal, was to keep that servicing alive. So I wanted to just honor him and his memory there. So he's happily retired now, probably wishing he was still here working with us. So, but Goddard has a rich history of satellite servicing. So between all of the Hubble servicing missions, the 3 robotic refueling missions we're going to talk about today, and OSAM-1 that we're currently doing, it has been great to see the change and the evolution of servicing throughout the years. So just to give you a little background of how RRM actually came about, after the last HST servicing mission, we were sitting with CEPI doing a lessons learned, talking about what we could learn from Hubble that could be applied to future servicing. And CEPI looked at me and said, well, if your team can build tools, I'm getting a little feedback on that. Do you guys hear that, or is it okay? He said, if your team can build tools for astronauts, you can most certainly build tools for robots. So go off and figure out how to develop tools to do robotic refueling. And we'll figure out how to get this demonstrated. So we came up with a concept, and we went and met with the Canadian Space Agency because we knew we wanted to do this demonstration on the International Space Station and take advantage of the robotic system on the space station. If you're familiar with it, the special purpose Dextrous, are we going to start rolling the images just so in case you guys can see it? The special purpose Dextrous manipulator on space station is the 2-armed robot on ISS. Each arm is 7 feet long. It has a standard end effector that has just a 7/16 socket drive. It's the only interface it has on it. So we met with the Canadian Space Agency and we asked them, we showed them the concept, the tools that we wanted to use, and they were a little bit leery about using SPDM for this because they said our robot wasn't designed for this. It was designed to do space station maintenance where we move batteries around, we move payloads from different locations. So they said it wasn't designed to do this type of dexterous manipulation you're looking at. Whereas we wanted to cut wire, remove caps, manipulate thermal blankets, and actually transfer fuel through the fill and drain valve. So we said, you know, just please trust us. We think it'll be a great partnership. Let us take what we've learned with Hubble servicing and how to build tools for astronauts in an astronaut gloved hand, and we'll build that innovative tool to bridge the gap between the end of SPDM and the interfaces that weren't designed to be serviced. And so they agreed, and it's been a great partnership. They started out by saying, we'll do it on one condition. We want you to keep the tasks as simple as possible. We only want to use one arm so that we can have the extra arm for stabilization, because they were afraid that maybe the forces and torques of the tasks that we wanted to do would get too high. And so we said, okay, we'll do that. Well, after we did, and we're going to go into a lot more detail here, but I'm just trying to give you the background. So after we did the first set of operations, they were like, oh, that wasn't so bad. So then they went from, okay, we won't have to stabilize, we'll just use one arm. And we actually culminated on RM3 where we just kept pushing the limits of technology. And I'm going to turn it over to Mark and Justin here in a minute to talk about some of these technologies that we pushed. But we actually asked them, we said, hey, we want to have tools in both arms. And they were like, oh, that's just like you guys. You just keep asking for more and keep pushing those limits. But so it actually culminated, and you'll see some images on here as if you're looking through the images on the screen of where we actually, on RM3, we had the cryogen servicing tool in one arm and the Viper tool in a second arm. So again, it's great to see that evolution and how we've really pushed the limits of technology while we've been doing this robotic refueling mission. So I'm going to turn this over and bring Justin in. Justin, do you want to give the group a little more background on RM1 and 2 and what we were trying to accomplish there?
Sure, Jill. So RM1 was a payload that was sent out to ISS on the last shuttle mission. The payload box itself is maybe 30% larger than your clothes dryer at home. And in that box, we put tools because we wanted to keep them warm. And inside was a fluid system because the purpose of RM1 is we wanted to show that we could refuel a satellite with a simulated fuel. On the outside of the box, there were a number of what we call task boards or busy boards where the tools that we flew within the payload that would be picked up by Dextrous, we could show that we could take things apart. So on the outside of this box, this RM payload box was riddled with satellite interfaces that enabled us in order to show that we had the dexterity to take things apart. Because we made these task boards modular and the tools modular, after they were used and demonstrated, it gave us the ability to replace those tools and task boards. And that's what RM2 was about, sending up additional task boards for demonstrations as well as tools to demonstrate as well. So RM1 was really about showing we could refuel. RM2 is additional items, including taking apart things more on the electrical side of the fence than plumbing side of the fence. Both were tremendous amounts of knowledge was gained about how to use Dextrous, how we develop tools, and our philosophy on how we use a tool with a robotic system and the interchangeable parts of those particular tools. The greatest example is we like to use a socket wrench. A socket wrench is very universal. So why not put different sockets on the end of that socket in order to perform that particular function? And that's what we kind of subscribe through, more modularity. So modular task boards, modular tools, and also the tools themselves were modular that we could put components on the end of them to whatever we're trying to meet up with. That's a wrap.
Okay, thanks. Mark, I'm going to turn it over to you. Can you give us a quick overview on RM3?
Sure. Thanks, Jill. So RM3 was kind of the next generation of the original RM payload. Again, it was a similar kind of washing machine-sized box that is mounted on the outside of the space station. So all these demonstrations, of course, are outside. It's not within the crew volumes. So it was transported up on a SpaceX flight, actually, and remotely moved over by the Dextrous robot into position. And the main focus of RM3 was to kind of get more into the cryogenic fluid servicing. It's kind of an important need for future missions going to Moon and Mars to be able to store and replenish super cold fluids. So we carried up a dewar of 42 liters of liquid methane, and it was at cryogenic temperatures like I think 93 Kelvin, so it's very cold. And of course that brought a lot of different challenges with it. Of course SpaceX was very concerned about hazards to their rocket, and so we had to go through a lot of safety issues and satisfy them that we're not going to blow up their rocket. We were able to accomplish pretty much all of our science objectives regarding the robotic tools needed to actually install these large hoses. We had like an 11-foot long hose we needed to move from the basically representing the servicing spacecraft to a refueling or a satellite that needed refueling. And then we also stored the cryogen without any venting for over 5 months. And that's another important issue that you're storing cryogens on the ground. They're kind of just in thermos bottles, and eventually they warm up and they start to vent out. And in space, we didn't want to lose that precious commodity, so we flew some electric cryocoolers to keep the cryogen cold at its cryogenic temperatures for the duration of the mission.
Thank you, Mark. I just want to point out to the audience and those online that the pictures that you're seeing behind you, all the pictures that we chose are actual demonstration on-orbit images. So these are not demonstrations on the ground. All of these took place on space station at different times over the last 10 years. So It's always interesting to see, you know, robots working in space, and so please enjoy there's a combination of some videos as well as some stills as you go through it. Please enjoy that as we talk. So talking about, thanks for the overview on the development mission. So can one or both of you tell the audience a technical challenge that had to be overcome in order to push the limits of technology?
Want to go first, Mark?
Yeah, why don't you go first?
Sure. So as far as technical challenge, I brought with me a typical satellite fill drain valve, and it is very simple for a technician to open a fill drain valve and supply a satellite full of its fuel, and to close it all up and launch it. It's never seen again. Accessing that valve in space is a very large technical challenge because we had never done that before. And because we flew RM1 for the purpose of showing that we could refuel a satellite, it made us take apart these components with robotic tools that were not meant to be used. So because of just one example of using one of our multifunction tools, we had to develop an adapter that looks just like this. This sole purpose was only to remove the cap of this fill drain valve. So because of that, that is just one element. There's also lock wire, additional caps underneath there. Then you need to open and close the valve. So each one of these are very large technical challenges for us. And then in the end, once it's all open, we had to figure out how do we plumb a hose to a refueling tool in order to connect it and then activate our fluid system to flow fluid across that interface. Very, very challenging across the board. So that was very, very much of a challenge. Dexter had never basically had the experience in manipulating hoses, so moving that fluid hose around was new to them and new to us as well. But by ground testing, we were able to figure out the best and appropriate way to do that. Also moving harnesses in space, which is kind of like a hose, that also was technically challenging. We did that on RM2, where we're moving electrical connectors from point A to point B. A harness was being dragged along. That drag along harness in robotics is an extra force that I wouldn't say is typically there, but needs to be accommodated for. So those are two examples that I could give. Mark, do you want to go for it?
Yeah, actually, I would like to add to that. I was going to say one thing that when we first started this, you know, we knew we wanted to do several very different tasks. And for RRM, we came up with 4 different tools to do those. And we also needed to develop a means of stowing all these tools. And at the time, little did we know, we were actually going to end up building a total of 10 different tools that all had a common stowage interface. So early on, we were trying to develop ways to, easily stow these tools and have the robot be able to pull them out. And looking at previous examples there was a few tools that the ISS robot already used. They all used kind of the business end of the tool to grab onto their stowage locations. And since our tools were going to be so diverse, we really didn't want to go that way. So we ended up kind of designing this cage around the center of the tool, and that cage had like different interfaces on it, bayonets and a cleat interface that could be used to stow it to a structure, and that kind of stowage structure could be reused for all the additional tools that were flown after that. And it was kind of like developing a standard that was repeatedly used.
Good examples. One thing that came to my mind was you guys were talking about this is the NExIS camera and the Wi-Fi on RM3. For on RM Phase 2 and RM Phase 3, we flew what we call Viper, visual invertebrate posable something robot. It's easier to say Viper. So anyway, at the end of that, there's a borescope that's on you can be deployed about 3 feet in length, and the last 3 inches of it are deposable plus or minus 90, and you'll see it in scrolling through some of these images. But the camera on there is actually the smallest camera that was ever flown in space. It was developed for us by a company in Israel that was using it for medical purposes, colonoscopies, et cetera, and so they modified it to be able to fly in space. So on RM Phase 2, we flew a standard version of it, but we wanted to upgrade that to high definition for RM3 to be able to get a better camera image. And what we used it for demonstration, like Mark said, on RM3, it was to demonstrate cryogenic replenishment. And we wanted to be able to demonstrate it on a payload or a satellite that wasn't designed to be replenished. And so we wanted to feed the hose down, be able to verify once we got the refueling, the cryogen servicing tool with the refueling hose into the refueling port. We used we fed the Viper tool down through what we call the inspection port, and we had it sit in the opening to be able to show, we could verify that the fuel hose got into the right location. So anyway, as it was going down, we thought, hey, a high definition signal would be much better, give us better clarification of what we're seeing as we're going through the interfaces. But we had to develop a Wi-Fi system, and you think Wi-Fi, heck, we all have been using that on the ground for how long now. But developing a Wi-Fi antenna and the hardware for space, and to be able to communicate on space station and communicate back down to the ground. At the time that we did that was several years ago, was still a technical, we were still pushing the limits of what we could do, but we were able to push that and get some great imagery. So. So let's switch gears a little bit. Talking about the technologies, can you tell the audience, or what is the value of testing in microgravity or on ISS versus testing in 1G? What can be done differently?
Take it again. So in the microgravity environment, I would say the largest difference is the lack of gravity and the illumination of things on orbit. So the best asset a roboticist can have is visual assessment of what's going on. You cannot do it in the blind. You can do automated work robotically in the blind, but when you're manipulating interfaces, you really need to be able to see what you're doing and even have more than one camera to give you the perspective of depth to grab something. So the behavior of hoses and harnesses in space, and the microgravity and the illumination of them are huge factors that you really cannot test on the ground. So our testing up on orbit has been so rewarding for us to understand those ever-changing thermal environments and the illumination as well.
Actually, I want to bring up just one example. On the Viper tools, as Jill mentioned, we flew the first one on RM, and we flew up a second generation version on RM3. And one thing we noticed on the original Viper camera was some of the images were kind of shaky. And after doing an investigation, we actually realized that there is a zoom lens. So there's some optical elements inside one of the inspection cameras that was kind of used from existing ground cameras. And what we did is we replaced any components that were not space rated. And one of those components was the grease that the vendor had used. And on the ground, the grease kind of held those elements pretty much firmly in place. But when we stripped that out and put in space-rated grease, it was slightly thinner, and it was not very noticeable difference on the ground. But when it was in space, these optical images were actually floating and causing this slight jitter. And after we noticed that on orbit, which we did not see in our test program on the ground, we were able to correct that and do some additional testing of the Viper 2 unit and kind of solve that problem. And I think we have a more robust camera it's just from using that microgravity lab that we had on space station.
Thank you. So watching these robotic tools work in these robotic operations, can you describe for us how the tools and robotic procedures are developed for these missions?
So the first notion, obviously, is for us to identify what our particular task is going to be, and then we have to see whether our tools can support that particular requirement to perform that task. Hopefully, we could use one of our tools called the multifunction tool, which that's your socket, if you will, and we just have to create a new adapter to adapt to that particular interface. We use facilities here at Goddard that are right up the hill from us, our robotic facility, where we have robots that simulate the robot on ISS, the Dextrous robot. And in that, we use that as a development test bed for developing our tools. And also, our tools are only as good as the mock-up hardware that we provide. So it's very important for us to develop mock-ups that basically represent the interface that we're trying to take apart. So we use our robotic facility here in order to develop tools. After the tools are developed, we move into procedure development, where we have to have the steps that we are sequencing through in order to develop a procedure in order to use the tool and or the adapter attached to the end of it. So we do that pretty much within our community here at Goddard, within our division. We also reach out to the robos at JSE and those at CSA, Canadian Space Agency, who actually are the ones that fly the robot, Dexter, from the ground. We bring them here to our facility, we test here, and we run through those procedures and tweak anything that we feel is necessary. And then often we would then go up to Canada to a facility at the MDA, McDonald Weiler Associates, and they have a full-up mimicking Dexter ground test robot that we would put our tools and bring our mock-ups to further develop the testing as a training opportunity for flight.
So, Mark, leading from that, do you want to describe then for the audience how the robotic operations are actually done? How do we here at Goddard play a role in that, and how are they done in space?
Sure, yeah. Actually, we have a control center in this building complex, in the basement of Building 14, that we've used. So we have communications, video, and audio with the robot controllers that are in Houston at Johnson Space Center. Again, the actual people controlling the robot are in Houston, so it's not the astronauts, on orbit. It is controllers on the ground in Houston, and we're in constant communication with them. And then we also have a team at CSA up in Montreal that is also following along during the operations, mainly kind of keep track of the health of the robot, and we're verifying forces and torques and ensuring all joint angles are within legal limits, basically. So we're kind of following along, and there's detailed scripts that the robo operators are following, and they kind of contact us when there's questions or things that don't look quite right and they need support with. But basically, we're just following along through as they go through their robotic procedures.
We've heard through the grapevine over the years that the RRM series of missions, all the robot operators were fighting to get onto our tasks because this was some of the coolest stuff that they got to do with the robot on space station. So whenever they were staffing up the team for the next set of operations, they were always trying to get on the team. So they're always excited. They were always very excited to do the different type of work. And for those of you who don't know how the robot is actually commanded, for those of you who play a lot of video games, it is not with video game controllers. They still actually type in a command on a keyboard, move 3 centimeters plus X, or et cetera. So it is all typing and hitting the go command once everybody's at agreed. So it's like watching paint dry. Everything that you're seeing here is sped up multiple times for your viewing pleasure. Otherwise, we'd be here several hours. But so yeah, it's exciting though to get to watch and see how it all operates. So moving on, let's go to lessons learned. That's always a good topic. Can one of you or both of you share a lesson learned that you think can be applied to future missions in space servicing or assembly or manufacturing?
I can take that one if you want. I think one valuable thing we learned on definitely RM3, where we were doing a lot of operations with the long hoses. This is something that's, it's hard to get a sense of how they're going to act when you're doing the ground testing, just because of the zero gravity, impact. And when we got up there, we actually did 2 different hoses on RM3, and they both kind of reacted in ways that we didn't expect on the ground. So it was very valuable to use that platform to test these out. And I think there are some procedural things that we've identified that we can apply to future missions that are going to be using hoses in future servicing missions.
So, Jill, I'll further add to lessons learned. Our division is called, partial satellite servicing. So our plug is when you're dealing with building a vehicle that's going to outer space, let's make sure that you make it modular and serviceable, because that will be your friend in the end when there's an issue, something that is broken that needs to be repaired, or something that is obsolete that needs to be upgraded. So the plug is to make your device modular so we can come and service it. Another thing is take pictures. We like to see a lot of pictures of the hardware, because once you button up and it goes away, you really don't have that opportunity to get what the closeout photographs are. And we use those, and we've studied photographs for hours just trying to find all the different little nuances that aren't captured in drawings. So photographs go definitely a super long way. Another lesson learned from a Goddard perspective is that Goddard is so diverse and has so many resources. The lesson learned is there is someone at Goddard that can help you, and it's just not your division doing the work. So we really rely on the center to support us for all these activities. There are people out there to support us across many of the disciplines.
So I have two other quick questions. One, in addition to servicing technologies, Justin, this one I'm hoping you can address. Can you tell us what other technologies, and this kind of goes along to Goddard being diverse, what else did we fly on RM3 that you would like to share with the group?
Oh yeah, so we should definitely mention a ride-along on RM3, Mark, if you don't mind me talking about RM3. It was a compact thermal imager. So if everyone's familiar with the SWAP-C, which is small weight and compact, basically for cost, we flew a very small, lower cost, very small package infrared camera, and it was based on the instrument design lab here at Goddard, who made a new technology, strain layer superlattice detector. And what we did in order to get it down to the Kelvin temperatures is it had a very small cryo cooler that was attached to the back end of the detector to cool it down. So we were able to take this entire very small package, put it together. There may be a photograph in the slides that you see here. We were able to put that on RM and fly it on ISS. And through ground command, we were able to take a number of hundreds of photographs of this IR camera looking down at Earth. And the camera had two different modes, a water mode and a fire mode. So the water mode was searching for evapotranspiration, which is the water usage on the ground. And the other mode was it was able to detect hotspots for fires. So this was a very successful package that we added onto RM, and it won an Instrument of the Year in
Technology of the Year last year. So shout out to Mersey and his team for a great job. And we were happy to be able to support it on RM3. And yeah, you'll see an image of one of the superimposed images from the ground and what was taken on orbit. So if you look at that. So partnering, again, I think partnering was something that we really enjoyed on RM. So can you share with us, like what partnering with other centers like Glenn, how are we able to take advantage of that and advance some of their technologies as well?
Yeah, I can talk about it. We did partner with Glenn Research Center for a radio frequency mass gauge that was integrated inside our source door that had the liquid methane inside it. One of the challenges of dealing with liquids in space is trying to figure out how much liquid is actually in the tank, because you can't just use like a dipstick or something that tells you the height of the fluid, because it's floating around. And Glenn Research Center actually developed a kind of novel way of using radio waves to bounce off the edges of the fluid, and just looking at the signatures and comparing it to a full tank or various levels, and could actually get an accurate interpretation of how much fluid was in the tank from this new technology.
Justin, was there another example you wanted to share?
Yeah, sure. So I also should share with Glenn, we developed a specific task board on RM2, and that task board had to do with solar cells. Glenn had partnered up with a couple of commercial companies that were developing what at the time new technology, solar cells. So solar cells, as good as they are, their efficiency is in the low 30%. So any single 1% difference in that capability is very large in the broad spectrum of, you fly a spacecraft, the solar array could be smaller because it's more efficient in generating power. So we were able to assemble a task board with a number of representative commercial vendors with these new technology triple junction cells onto our particular task board We flew up to ISS, and at a particular time, Dexter, the robot, picked up that task board and was able to point the task board at the sun. When it looked at the sun, we had another solar cell facing the sun. That power would be generated by the sun and would turn on our internal avionics box. Once that would happen, the electronic box would then take sweeping current and voltage curves of each one of those vendors' solar cells and the performance in space, looking in what they call air mass zero, looking directly at the sun. Afterwards, the task board was eventually brought back down to the ground. We hooked up our cable, we offloaded the data went back to Glenn, and Glenn shared those results with the community.
Bree, I have more questions, or did you want to turn it over to some audience questions?
Well, why don't we start the audience questions,
Okay.
and then we can go through them if
Okay.
you'd like. So for those of you in the audience here in person, of course, you can go up to either one of the microphones on either side. But I'll start off with this one question. So I'm going to use my knowledge of coming to see you guys over in the Robotic Servicing Center. So I do know from listening to you guys talk that there were 2 satellites that were always made to be serviced, Hubble and the ISS. But none of the other satellites that have been launched that are up in space are actually made to be serviced. So how much easier would it be if a satellite was cooperatively designed rather than not designed to be serviced?
I'll go ahead. So, good question, Bree, and she has heard us give this spiel several times in our lab as we do our tours. But yeah, so if you design it ahead of time, we can reduce the tool count. Like Justin was showing you, the fill and drain valve, in order to access a typical fill and drain valve, a non-cooperative or not designed to be done robotically, fill and drain valve, it takes up to 7 different tools to be able to cut the wire, remove the series of caps, then actually do the, and get through the blanketing. So if that was designed to be cooperative up front, where you put a Velcro tab instead of tape that had to be cut, or, so you could just pull the blanket back with the tab, or you put, and you use a cooperative valve, we could get it down to 2 tools. So it would make a big difference in cost and time savings if we were able to get to the point where we were using cooperative hardware. So hopefully with industry, really the burgeoning industry here with in satellite servicing and working with Confers and our folks and the other government agencies, we can go to standards and we can start getting where each of the spacecraft is designed with a a cooperative valve, a blanket design that's easily manipulated, and as Justin also talked about earlier, modularity. If your spacecraft is designed with modular ORUs that can easily be taken out, like Hubble was, or again, ISS is a prime example of how you can, with international standards, be able to move things around. So if you do that in the beginning, it definitely will make your spacecraft easier to service in the future. So, you guys have anything to add, or we'll go to the next question?
So I'll just add something very small. What it really comes down to is time, return to service. So satellites are there to do something. So if they need to be refueled, that means they're complete, they're almost at their end of service. So the quicker you can get to a satellite, the quicker you could get it back on its way, it's back into operational mode. So robots take a long time to do the work if it's not cooperative, but if you make it cooperative, there is a lesser timeline for getting it back into service for what it was supposed to do.
Thank you, guys. We're going to turn it over to the in-person audience. Go ahead, sir.
Okay, this mic's on? Thank you. So, Justin, I have a question for you. You mentioned modularity, and I have to acknowledge, as Jill did, Frank Zappolino, because that was his mantra. I mean, that was who he was throughout the years. And you mentioned how the modularity of your hardware development evolved into specifications and standards. Now, I want to ask a question about examples that you have that have moved from our RRM to either OSAM or RSGS or into the industry. Specific examples of standards that you know of that are being applied currently.
Dennis, I know you asked that of me, but maybe Jill, you want to feel that as a larger question.
So the first standard off the books that's being done with Confers is the Cooperative Refuel valve. So if you go to the AIAA, that's the first one that is actually out for, that they've worked on. The second one that they're currently working on that we're applying towards, that we've done, we started on RRM and is applied to OSAM and also to some other satellites, is the fiducials. So on RRM, starting for the course, gosh, we flew, I don't even remember how many different types of fiducials, all different patterns, and we took advantage of all of the, the day, orbit, night, and be able to get the shadowing effects on those fiducials, and we tested all of that against our ground algorithms for pose estimation. And so we gained a lot of experience, and we've been able to transfer all that experience on as to which tags or which fiducials, or which shape and which pattern actually works best for which type of task. And so we now supply those fiducials to other spacecraft providers, and so that's one of the first examples of how what we did on RRM is now being used in industry. Does that?
Yeah, thank you. And I have a follow-up. Didn't you fly fiducials on James Webb too?
James Webb as well. Yes, there are some on James Webb. That was one of the examples. There will be some on Roman as well. So yes, Goddard. We are working with a lot of the Goddard projects now to make sure that they're on theirs. It's simple. It's easy to do. Low mass, low dollar.
It's cooperative. Does that make the satellite cooperative in your perspective? In other words, you have cooperative systems that allow you to use, or that a satellite manufacturer could apply that'll support your systems and hardware development.
Am I taking this again? So yeah, good question. So there is what we call the servicing spectrum, that if there's lower levels of cooperative versus fully cooperative, and where you were going is that just flying a fiducial gets you at like the lower level of cooperative. It doesn't make it fully cooperative. You really need to go through that whole servicing spectrum where you're building up to the actual cooperative servicing valves to be fully cooperative. Full modularity, full cooperative interfaces, thermal blankets that are designed to be manipulated to be fully cooperative. So so there is and we can share it or we can post it, but yeah, there is a servicing spectrum that we provide that shows what levels of cooperative, and you can pick and choose depending on what the funding level is, or what you can put into your spacecraft to be able to make it cooperative. So, go ahead.
Great, thank you. So now we're going to take a question from online. So how hard will it be to adapt this technology to all different types of satellite propellant? Not everyone at one time.
Go ahead, or I.
Well, I mean, for us, the fill drain valve, making that cooperative is something that we would like to see commercial satellite vendors moving towards. And of course, we want to make that available to folks as far as licensing to get that product to make the satellite. I mean, it's kind of like where Dennis was going and Jill about the spectrum of servicing. There are many checkboxes to make that happen for fully serviceable, whatever that accreditation would be. Having something, specifically if you're going there to refuel, having a cooperative fill drain valve, saving less tools, less time getting back to service, that is one element of the many broad things that you could do. But to me, the fill drain valve would be good.
Yeah, so to add to that, like we have a design for a cooperative service valve that can not only work for hypergalls, it can work for biprop, it can also work for xenon gas, and then we also have another design for cryogenic fluids. So, so I think that throughout the development of RRM, we've been able to look at multiple different types of fuels, as well as not just RRM, but our other servicing technology development with respect to OSAM-1. We've been able to develop different types of cooperative valves for different types of fluids. So we do have those available, and we've been sharing those designs with industry as well, because there are a lot of companies that are interested in different types of fuels. So we've been able to pass along that knowledge.
And some of the changes are fairly minor. There's like different seals and organic materials for different, fuels and things that are fairly easy to change out. And then, of course, the cryogenic fuel is a little bit different to kind of keep that at lower temperatures, so that is kind of unique.
So you mentioned the industry partners when you were talking about fueling. So how does NASA and specifically your organization work with the commercial sector on robotic servicing?
So great question. Goddard has a really great technology transfer program. So we work closely with our friends over in the office and our patent lawyer friends as well, who help us to patent all of our technologies and make it available for licensing. So yeah, we get a lot of requests to be able to take advantage of our technologies. We host an industry day once a year. We've been doing this, gosh, now what, for the last 4 years now? And so we recently started partnering with Langley and Marshall. And last year was held at Marshall. This year we'll be back here at Goddard. So look forward to that. Hopefully you all can attend. But anyway, yeah, so in that we invite all of our industry partners, other government agencies to be able to come, and we present the latest technologies that we have developed and tested and qualified and are ready for transfer. And so we keep that technology portfolio up to date. So if you're interested, please give us a call. We're always happy to walk people through the technologies that we've developed. But yeah, we really like supporting our commercial industry friends, and there are a lot of companies, and especially it's really nice to see a lot of the new startups that have great ideas, and they've got a lot of young, real creative, innovative people that want to work in satellite servicing, and so it's a lot of fun to be able to talk to them and share our knowledge and see their ideas and where they're going and how they can support the industry. So it's a lot of fun watching this evolution, as we were talking about earlier.
Thank you. So let's talk about practicing, because we don't just send these things up onto the ISS without practicing what we do first here on Earth. Do you use virtual reality to practice, or how does that work?
Justin, Mark, go ahead.
Actually, we haven't really used virtual reality other than 3D CAD models and doing checks with that. But we do have a simulator for the end effector from Dextrous, the ISS robot, and so we can test all these tools in our own lab here at Goddard, and measure forces and torques and kind of get right up there and see how the tools are interfacing with the different satellite systems, and so that's kind of been very valuable. We have the engineers right there working with these robotic demonstrations and can learn and adjust the tool designs to accommodate.
One of the nice things, let me add to that, one of the nice things that we've been able to do with having these facilities here at Goddard is when they're doing the robotic operations on ISS, we have a team here doing the same procedure at the same time. And so if for some reason they're misaligned or they're trying to figure out if they bumped into something, we've been able to walk them through and say, oh, hey, we can see this in the ground system versus, or try this or bump it this way. And so it's been really value added to be able to do that in real time, to be able to have the systems and be able to follow along. So it's a great learning experience, and it's really aided in our ability. If you're looking at these videos and you see all the different the markings on there, it's been test and retest to determine what looks best in the camera views, what can the operator see best when they're trying to do these manipulations. So I think that's one of the key things, Bree, that we've been able to do is in preparation and testing, is to be able to try all these different types of camera views and these different angles and be able to see what works best by using our ground test facilities.
Great. So you did mention that the satellite servicing, or NExIS, was born out of the Hubble servicing mission. So obviously those tools and technologies were meant for astronauts to use. So what are some challenges and then opportunities that you guys have using robotic servicing compared to the astronaut servicing?
So I'll give one example because I just saw the video. On RM2, we flew a task board that had here it is, an electrical connector. This is an electrical connector that's coming up to a receptacle and basically mating that connector. It is hard enough for an astronaut to do that wearing basically hockey gloves or an astronaut glove, which is big and bulky, because the crew member needs to look at that connector and find out on the inside of the connector what is called a master key, the biggest tooth out of a couple of tooths around the electrical connector. And they have to make sure that is in the right position when they're mating the connector. So you got an astronaut thinking about what he's doing, looking right there, mating it up. On a robot, that is so difficult to do. But because we are flying something that we brought with us, in this case, as you see that orange adapter right there, yellow adapter, we were able to put lines to tell where that master key was. So because we added fiducials, we made something that is extremely difficult to do, even with an astronaut. It was done with a robot.
Yeah, I'd like to add, one of the key things for robotic servicing is you need good views of what you're, manipulating. And, early on we decided to have these, set of 2 cameras. So a lot of the camera views you're seeing in the video are from tool cameras that are right looking at the tip. So we had 2 orthogonal views of the work site, and that really helps the operators, to be able to figure out which way to move. And that's, with astronaut servicing, your eyes are right there. It's easy to figure out.
But one limitation I do remember when we did like SM4 and they had to look around, they had to try to get into some of the corners. It was hard for the astronauts with the helmet, and they only had the cameras on, the sides of their helmets. It was hard for them to be able to get some of the views. So there are advantages and disadvantages, but I think the goal is that, or I think the key there, I always think of Bree, is when I'm asked that question is having both of them together, working together would be ideal, because you can take advantage of, the astronaut's ability to be able to adapt to the different situation and be able to take advantage of the robots, maybe being able to reach into different places that the astronaut can't reach due to the limitations of their suit. So I see advantage of having, both working together to really make for a, great viable servicing missions.
Thank you. So let's go in the room.
Yeah, so following that question, during the Hubble missions there, and for about a year, we looked at a robotic mission here at Goddard across the agency. A lot of folks said it could be done. A lot of folks said it couldn't be done. I'd be interested in your thoughts now, having done RM for a year or 10 years, what you think about the possibility of that mission and anything you learned from RM that was easier or harder as applied to Hubble when you were thinking about it, back in the 2000s.
It's an interesting question. You want me to take that?
Sure.
Yeah.
Okay. So, I remember presenting in front of several independent review teams on Hubble robotic servicing mission. And I agree with you. There were a lot of people that said the technology wasn't ready. We would never be able to do what we did here on RRM. So I think it was just a matter of, breaking the tasks down, to start by breaking it down into simple, small steps, and just, how do you do each of those steps? Sometimes it's overwhelming when you look at it as a big problem, but when you break it down into the smaller steps, you can really, we were really able to be successful. And so that's what we did on RRM, was just, step by step, how do you tackle cutting wire? How do you tackle removing a cap? And just moving forward one at a time to be able to show that we were successful. So I think where I was going in the beginning is the technology has advanced so much that, it's great to see now that, it's commercial industries, that look at how many commercial industry or how many commercial companies now are looking at this technology and how to take advantage of these technologies and to do in-space servicing to really get advantage of the life extension. And so it's been nice to see a change where, like you said, when we were looking at Hubble, so many people said the technology wasn't ready and it couldn't be done. And here, just 10 years later, we've been able to demonstrate multiple different technologies on ISS, as well as we're developing, OSAM-1, which is a full-up refueling mission to go refuel Landsat-7, and there's been a lot of commercial successes. So, again, the paradigm is changing, and let's hope we can keep that paradigm moving forward and get rid of the one and done. And if we can start applying these modular and cooperative interfaces into these new designs, we'll be able to take advantage of these technologies even more. And it'll be interesting to see how in-space operations change by taking advantage of these technologies.
So as a closing question for each one of you, we were talking about 10 years of robotic servicing today. Where do you see robotic servicing in 10 years, 20 years? What does the future look like?
Go ahead.
So, Bree, good question. So 10 years ago, we didn't have, maybe there are a few, electric cars. And we also didn't have private astronauts flying to space. So here we are 10 years later, and look where we are. So satellite servicing, I think it's going to be a little more in 10 years before that's more the norm. But it is definitely coming. We could call it progress, technology proceeding along. That's my thought.
And I also think, that things are going to be moving farther away from Earth. We're going to have missions around the moon and Mars, and I think definitely robotic servicing has a good role in that to kind of, relieve astronauts of some duties. But again, if you go farther away, you also have this latency issue where I don't see, it's more difficult to have controllers on the ground on Earth, trying to manipulate things just because it takes so long to send and receive signals. So I think it's kind of, as Joel was mentioning, it's kind of like a synergistic to have astronauts and robots working together to service future satellites.
So it's kind of like when I answered your question, Brian. I think we're going to see great advances in the next 10 to 20 years. I think that it is hopefully that paradigm keeps changing. We're just starting to where people are coming to us and saying, hey, how can we incorporate this into our designs? How do we make this serviceable? Whereas we weren't getting a lot of those types of questions 10 years ago. We were still proving the technology was ready. So hopefully in the next 10 years and by hopefully 20 years, there's requirements that are being flowed down into spacecraft to be able to make them serviceable, or make sure a level 1 or a level 2 requirement that your satellite shall be serviceable. And what does that mean? Not just serviceable, but cooperative. And so making sure that those cooperative valves, and as we were talking about with standards, as these standards get developed and released and approved, then we'll be able to, and if we can get each of those things on the servicing spectrum qualified and readily available for spacecraft builders so that the cost of a cooperative fuel valve costs the same as a standard fill and drain valve, then that's where we want to see this go eventually. And hopefully by the 20-year time frame, that's where we are, is that all of the cost of cooperative is the same as the cost currently, so that the spacecraft providers can meet their requirements. Hopefully they have requirements and they can meet those requirements with no additional cost to their missions, but yet they're taking advantage of the ability to be able to be serviced and extend the life of those satellites in space. So hopefully that addresses your question, Bree.
Perfect. Does anybody have any additional comments before we close?
I'll just add one more. So there aren't going to be less satellites in the future. I do have one more thing that I was going to add that made me think about it as you guys were talking, because Mark kind of referred to some of the future work. The one thing that I think I want to make sure we talk about today is not just satellite servicing, but these technologies that we're talking about with respect to modularity, cooperative valves, being able to do some of the types of work where, changing out batteries robotically, refueling, et cetera. These can also be applied to, Artemis and the lunar surface, ISRU systems. So I want to just make sure that we get that out there, that this is not just extending the life of satellites. The technologies that we've been developing, the techniques, the tools, these are all applicable to lunar surface applications as well, so that if we've got robot systems as well as astronauts on the surface of the moon, they can work together to be able to, again, upgrade habitats, maintain the habitats, upgrade and maintain ISRU systems, instruments, etc. It'll be nice to be able to see how all of this can be used on the lunar surface applications as we move forward into that program, as well as eventually go to Mars and be able to do more work on Mars planetary. So I see this as an evolution of not just satellite servicing, but also taking these technologies and expanding them into Artemis and moving forward.
Well, I want to take a moment to say thank you to each of you for joining us today, especially with this new hybrid model. You guys were great to come in. And thank to everybody who came in person in the auditorium and joined us virtually. So that concludes our panel for today, but please make sure that you check Dateline and your email for next month's Engage session. Thank you, everyone.
Thank you.